The concept of space is familiar to all of us. Generally speaking, the knowledge of the average person is limited to some basic facts about our system and the universe around it. But the most exciting things in the cosmos take place in remote areas not readily available to our eyes. And if we look beyond the boundaries of the solar system, a fascinating picture of infinite space opens up to us. Today, I invite you on a journey to these mysterious places, realistically quite beyond our physical reach. As we get further away from our Earth, we will be braving the most forbidding areas of space. Our flight starts in the vicinity of Titan. Then we will move on to the most dangerous asteroids, and a bit later, take a look at Pluto. Right after that, we will set out to observe some potentially habitable exoplanets, check out the microquasar SS-433, and then see what intergalactic space looks like. As our journey draws to an end, we will consider the future of our universe and try to predict what will happen after its demise. Apart from the Earth, Titan is the only celestial body in the solar system with liquid on its surface. Unlike our Earth, however, this liquid isn't water but a mixture of liquid hydrocarbons, mostly methane and ethane. Oceans on Titan were first seen in radar images being backed by the Cassini probe on the 21st of July 2006. In the period from 2004 to 2017, the space probe approached Titan on 127 occasions. Thanks to these photos, scientists were able to successfully map out the entire surface of this moon in fine detail. Analysis of the relief and its features revealed that the same processes were instrumental in its formation, both on Titan's and the Earth's surfaces. The only difference lies in the fact that water was the main factor for relief formation on our Earth, whereas on Titan, it was liquid hydrocarbons. As a result, Titan's surface is also covered by lakes, seas, rivers, and bays, just like that of our planet. It also rains there on a regular basis. Titan's lakes are mostly rather vast but not really deep, with their number reaching 650. The biggest of them are referred to as seas or mares and have been dubbed after mythical sea creatures like Kraken mare, Ligeia mare, and Punga mare. There are dunes on Titan's equator, which is explained by the fact that the climate in that area is the driest. These areas account for 17% of the overall surface of this moon, with mountains and labyrinths making up 14% and 1.5% respectively. Most of Titan's surface, 65% to be precise, is covered by plains. As for mountain ridges, they stretch for several dozens of kilometers with a height reaching several kilometers. Only 23 impact craters have been discovered on Titan, with a diameter of over 20 kilometers, which is not more than 0.4% of the total area. Most craters are believed to have disappeared due to highly intensive erosion processes that have been taking place for several 100 million years. Due to some organic compounds which include nitrogen atoms, Titan and its atmosphere have an orange hue. Titan, Saturn's moon, has several large bodies of liquid on its surface. The largest one is called Kraken mare, with an area of approximately 400,000 square kilometers and a length of about 1,100 kilometers. It is located in the northern hemisphere and is estimated to be up to 200 meters deep. The second largest body of liquid is called Ligeia mare, also in the northern hemisphere, with a width of about 500 kilometers and a depth of up to 170 meters. It covers an area of approximately 100,000 square kilometers. The third and smallest sea, Punga mare, is also in the northern hemisphere and has a diameter of approximately 380 kilometers. These seas are made up of liquid methane and ethane, which are abundant in Titan's atmosphere and form dense clouds. Sometimes dark spots can be seen on Titan's surface, which are likely drifting chunks of ice. Hydrocarbon ice typically floats at temperatures close to minus 183 degrees Celsius. If the temperature drops even lower, the ice sinks due to the presence of nitrogen bubbles. It is possible that in some areas of Titan, there is an ice shield enveloping liquid methane both below and above. The chemical composition of the liquid on Titan varies depending on the area due to the presence of liquid gases with different boiling points. The composition is largely influenced by temperature. It is worth mentioning that there may also be a subsurface ocean on Titan, possibly containing water. This hypothesis is based on the idea that Saturn's tidal effects heat up the core, creating high enough temperatures for liquid water to exist beneath Titan's surface. Cassini's images from 2005 and 2007 showed that some relief features had shifted, suggesting the presence of a global liquid layer separating thought to contain ammonium, which acts as an antifreeze, lowering the water's freezing point. Coupled with high pressure from Titan's crust, this may create favorable conditions for the subsurface ocean. The depth of the ocean varies across Titan, and in some areas, the liquid freezes and forms an ice crust. The high salt concentration in certain areas makes it inhospitable for life. However, Titan's atmosphere is dense and chemically active, containing diverse organic compounds, raising the possibility of life in the upper atmosphere. Layers it seems feasible that simple organisms could be sustained by gas hydrogen and also consume molecules of acetylene. After digesting these in return, they could produce methane. It should be mentioned that relatively recently highly active organic molecules were discovered in Titan's atmosphere. The substance in question is called cyclopropanoidone. This is an unstable and highly active material which cannot be observed on Earth anywhere but in a laboratory environment. Scientists first came across it in 1985. And clouds of interstellar gas in space, cyclopropanoidone is crucial in forming larger organic molecules. Its discovery on Titan was the first case of finding it in the atmosphere of a planet rather than an interstellar environment. This discovery will certainly help scientists to see Titan's chemical evolution from a different angle. There are also some alternative theories about life on this satellite. According to these, there could also be life forms in liquid methane rivers, but this is feasible only on condition that these organisms live on hydrogen rather than oxygen and produce methane rather than carbon dioxide. Unlike organisms on our Earth, however, since Titan does not lie in the Goldilocks zone and its surface temperature is as low as about 180 degrees below zero, these hypothetical organisms would differ a lot from those we used to see on our planet. Lipid cell membranes, for instance, which are typical Earth dwellers, wouldn't be able to survive in such conditions. Some really bizarre analogs would then be produced by evolution processes, and we can't venture even a wild guess as to what they would be like. Be it as it may, climatic conditions on Titan really are able to sustain certain forms of microbial life. This is the main object of interest for NASA's Dragonfly spacecraft, planned to be launched to Titan in 2027 to investigate, and who knows, perhaps this mission is destined to reveal something even more fascinating than we've already found out. The search for alien life forms is undoubtedly an arduous task that will probably not yield any results until the next millennium, but its global significance can hardly be overestimated. If at some point we succeed in our attempts, this will be a major milestone and the beginning of a new era in the history of mankind. It will not only allow humans to enhance their own knowledge, but also begin a long and scrupulous process of fostering relationships with intelligent beings from another world. Large objects do approach our planets now and then. For example, on the 14th of November 2020, asteroid 2024 with a diameter measuring about 10 meters past our Earth at a distance of 383 kilometers from the surface that is below the International Space Station. And most satellites, even though known potential threats, are monitored by scientists at all times. The problem is that most asteroids are rather dark objects whose dimensions are quite modest by space standards, which makes them hard to detect. However, an explosion caused by an impact of a celestial body with a diameter of just 10 meters would be tantamount to the atomic bombing of Hiroshima. It may not leave any radioactive waste, but a blast this powerful would wipe a little town right off the face of the Earth. An asteroid with a diameter measuring 50 meters that is as big as a modern multi-story building would unleash a power of several dozen kilotons on impact, which would be enough to raise an entire city almost to the ground. If an asteroid this large were to fall into an ocean, it would cause a tsunami reaching up to 10 meters, which would drink destruction all the way it went, traveling for hundreds and thousands of kilometers from the site of its impact. Were this asteroid's diameter to measure a kilometer or so, it would cause mass destruction throughout an entire continent. The force of the explosion on impact could reach as much as thousands of megatons in intent equivalent, and its consequences would haunt the planet for many years. Civilization would not survive a calamity of this scale, nor would other living creatures, with the only exception of protozoans and exceptionally enduring organisms. Mass extinction events did take place in the history of our Earth. The most notorious of them, Cretaceous Tertiary extinction event about 66 million years ago, It is posited that dinosaurs and a number of other species died out as a result of it, as for the most large-scale mass extinction event, it took place approximately 251 million years ago, coming in between the Permian and the Triassic periods. Based on results of paleontological diggings, it was estimated that about 90% of sea species and 70% land species died out as a result. One of the things that caused both of these dramatic calamities is believed to be the fall of a large asteroid today. The number of potentially dangerous objects is estimated to be in the region of 1.5 to 2,000, although this number may reach 4 to 6,000 according to the data provided by the WISE telescope. Since they're so small and dark, these celestial objects are rather hard to spot. For example, the size of the asteroid of 2008-3, which burned up in the atmosphere just above Sudan in 2008, was anything from 2 to 5 meters. It was spotted just 20 hours before it would have impacted the Earth, fortunately. Nobody was hurt. There is a special rating scale known as the Palermo scale. It is a generalized scale reflecting potential impact risk posed by this or that celestial body, which takes into account the body's kinetic energy and the probability of hitting the Earth. The higher the value, the bigger the threat to our planet. If a body's Palermo scale value is below -2, this body is practically safe. Asteroids with values between -2 and 0 do not pose any immediate threat, but require monitoring at all times. As for objects with a value above 0, they are realistically dangerous for the Earth at this point. There isn't a single celestial object out there with a positive Palermo scale value, and there are only 2 asteroids in the yellow alert zone that is their value is between -2 and 0. Both of them fall into the category of the Apollo asteroids, celestial bodies whose perihelion lies closer to the Sun than the Earth's aphelion, and whose orbital semi-major axis is bigger than that of the Earth. Thus, these objects crossed our planet's orbit from the outside. The Bennu asteroid designation, 1999-36, with a potential hazard index value -1.69, poses a smaller threat to the 2 in the year 2135. It will find itself just 300,000 kilometers away from the Earth, which is slightly closer to us than the Moon. Bennu's average diameter measures approximately 500 meters, and the asteroid's mass is anything between 60 to 78 million tons. If it were to collide with our Earth, the resulting explosion would be tantamount to about 1,000 megatons in tint equivalent, which would almost certainly cause major catastrophic disasters all over the planet. In 2016, NASA launched the OSIRIS-REx probe to Bennu in order to obtain samples of the minerals making up the asteroid. The probe is scheduled to get back to the Earth in 2023. The more hazardous of the 2 asteroids is 1950, though with a Palermo scale value -1.42 today, it has the highest probability of hitting our Earth. Its diameter measures about 1.3 kilometers, and its mass can be anything from 2 to 4 billion tons. 1950's orbit is elongated and elliptical, and it crosses the orbits of our Earth and Mars. 1950's closest approach to the Earth is expected in 2035, but a hazardous approach will take place only as late as on the 16th of March 2880. What would await us if the asteroid did impact the Earth? Let's assume no preventive measures have been successful to deflect this body, and the disaster is inevitable. An enormous chunk of rock with a diameter almost 1.5 kilometers and a mass that could be 2 to 4 billion tons heading towards the Earth at a speed of about 14 kilometers per second. This would be the speed of 1950 at the moment it hit the Earth. If an impact event did occur as estimated by NASA, of course, part of the matter making up 1950 would burn up and disperse in the atmosphere as the asteroid slowed down, and the main body would be likely to break up into several large rocks and a great number of small bits depending on their size. Each of them would cause an explosion of not less than 20 kilotons on impact for the Earth's crust. That's the average power of a modern nuclear bomb with a comparatively modest charge. The overall power of the explosions would most likely be over 1,500 megatons, with a bombarded area larger than that of Europe. All constructions within the radius of 300 to 500 kilometers would be razed to the ground, and even reinforced underground bunkers wouldn't guarantee enough safety. The energy of the shockwave would allow it to sweep around the Earth. If an asteroid were to fall into an ocean, it would cause a massive tsunami, with waves reaching 40 meters or higher. These tsunamis can travel for thousands of kilometers, causing destruction along coastal areas near the impact site. Multiple impacts would also release tons of dust into the atmosphere, creating dense clouds that block sunlight and cause a sharp drop in temperature, known as a nuclear winter. An impact of this scale would not only affect the Earth's crust but also the mantle. The shock wave would trigger volcanic eruptions and generate a second wave of tsunamis and earthquakes. The release of ash into the atmosphere would further contribute to temperature drops. While there is a popular belief that an asteroid impact would significantly alter the Earth's orbit or orbital period, this would require an object as large as the Moon or Pluto. However, even the largest asteroid in the solar system would not be enough to cause such drastic changes. The potential impact risk of the asteroid 1950 DA is currently estimated to be very low at 0.012. However, the impact probability may increase if the asteroid's orbit changes due to collisions with other celestial objects. In the past, it was believed that humanity lacked the capability to prevent asteroid hazards, but advancements in technology have opened up possibilities. Methods such as covering an asteroid's surface with a light-reflecting film to change its orbit, or using nuclear bombings or powerful thrusters to shift its trajectory have been proposed. The DART program, launched by NASA in collaboration with SpaceX, aims to deflect an asteroid's trajectory by causing it to collide with an artificial spacecraft. The demonstration will target the binary near-Earth asteroid Didymos, which consists of two components with diameters of 800 and 150 meters. The spacecraft launch is planned for 2021. While monitoring celestial bodies within our solar system is crucial, there is always a risk of previously unknown objects from the galaxy's outskirts approaching Earth. Some comets and asteroids have orbital periods lasting hundreds or even thousands of years, and their small sizes and dark surfaces make them difficult to detect. However, the likelihood of such a catastrophic impact event is extremely low. In fact, there are many other dangers on Earth that pose a greater risk to humanity. Pluto is the largest trans-Neptunian object in the solar system. It is also the largest object in the Kuiper Belt. Just like most bodies in that region of space, Pluto is mostly made up of rock and ice, and its mass is relatively small, approximately 0.22% that of the Earth. To get a slightly broader picture, let's compare Pluto with the Moon. Pluto's mass is about 6 times smaller, and its volume is about 3 times smaller. Pluto's total area is 17.7 million square kilometers. To put it into perspective, the area of Russia, the largest country in the world, is slightly smaller at 17.1 million square kilometers. As for Pluto's diameter, it reaches 2376 kilometers, which is 1097.6 kilometers less than that of the Moon. As for Pluto's atmosphere, it is mostly comprised of gases evaporating from the ice on its surface. Today, we know that its chief component is nitrogen. Apart from that, 2 other gases are methane and carbon monoxide. Under the influence of high-energy cosmic radiation, other more complex compounds form from these elements. Due to Pluto's surface temperature, these compounds are not volatile, such as ethane, ethylene, and acetylene. There are also the so-called tholins settling on the dwarf planet's surface, giving it a brownish hue. The average surface temperature on Pluto is 50 Kelvin, which is 223.15 degrees Celsius below zero. With every kilometer higher up, this indicator increases by approximately 7 degrees. So the atmospheric temperature is 40 degrees higher than that on the surface. This could be accounted for by the greenhouse effect caused by methane. We're used to thinking that Pluto's orbit is stable and unwavering. However, on closer observation, it transpired that Pluto's movement is rather chaotic and can be defined in non-linear equations. It takes a lot of observation to be able to detect that. When carried out in short time spans, observations reveal seemingly regular movement. In reality, Pluto's orbit slightly shifts in every period, eventually changing to such a point that it is impossible to retrace its initial trajectory. This dwarf planet's rotation is quite peculiar too. Namely, it is retrograde, which is also the case for both Venus and Uranus. It means that they rotate in the direction opposite to that of the other planets around the Sun. A day on Pluto lasts and small mass. Pluto is a rather challenging celestial object to study. Even very big telescopes show it to us as a tiny spot, seemingly not much different from a regular star. we have been able to acquire a certain amount of data with the help of the Hubble Space Telescope. Nevertheless, the greatest and most important portion of information was made available after the launch of the New Horizons mission. The first photo of Pluto was made back in September 2006, when the space probe was testing its LORRI camera. As the spacecraft approached Pluto closer and closer, more and more features of this dwarf planet were revealed to us. Thus, the object's surface was seen to be far from homogeneous. Albedo, that is diffuse reflection properties of the surface, varies from 10 to 70% depending on the area of the object, which makes Pluto the second object in the solar system, after Charon, in terms of contrast in albedo. This diversity causes periodic variations in Pluto's luminosity and spectrum as it rotates. The dwarf planet's interior must be made up of 50 to 70% rock and 30 to 50% ice. Its dense rocky core must be embedded in an icy mantle about 300 kilometers thick. According to spectral data, there is water ice on Pluto's surface as well, but it is mostly camouflaged by a layer of more volatile ices. There is also frozen methane and carbon monoxide, as well as traces of other compounds generally forming with methane and nitrogen when exposed to powerful radiation. Particular at that are ethane nitriles and phthalates, which make Pluto look brownish. On the 15th of July 2015, the New Horizons space probe flew by Pluto, 12,500 kilometers away from its surface. Both sides of the dwarf planet were photographed during the flyby, the one seen on closest approach and the opposite one. Thanks to these images, a vast heart-shaped area measuring 1,800 by 1,500 kilometers was identified. It was later nicknamed Pluto's Heart or Tombeau Regio. The left part of this area is believed to be a crater filled with crystal nitrogen. Also, 2 mountain ranges were identified in this area. The height of the first range reaches 3,500 meters, and it was named the Tensing Montes. The height of the second range, dubbed the Hillary Montes, reaches up to 1,500 meters. The most notable geological object found on Pluto is Sputnik Planitia. This trench is likely to be an impact crater with a diameter measuring 1,492 kilometers. Sputnik Planitia is filled with frozen gases and is streaked with a great number of grooves, which divide it into irregular cell-like areas measuring dozens of kilometers. There may also be cryovolcanism on Pluto. The last image taken by the spacecraft appears to be indicative of just that. The potential cryovolcano that can be seen in this picture was dubbed Right Mons. The surface in the picture is comparatively young by space standards and practically devoid of impact craters. This shows that the crust in this area was formed relatively recently, and if Right Mons really is a cryovolcano, its enormous size of 144 kilometers across and 4 kilometers high easily makes it the largest cryovolcano in the outer area of the solar system. Among other interesting features discovered by New Horizons, there is a blue stratified haze enveloping the whole of the dwarf planet. In the images, the haze is seen to reach over 200 kilometers high and is registered by the ultraviolet spectrometer to persist to the point of 300 kilometers above the surface. The haze is likely to be made up of particles of non-volatile elements that originate from atmospheric gases. These elements gradually settle on the dwarf planet's surface, producing this effect. The New Horizons mission is scheduled to continue until 2026. Apart from studying the objects in the Pluto system, the spacecraft has already provided insights into other Kuiper Belt objects insufficient for a dramatic change of course. The radioisotope generator's energy should be enough to last it for another 10 years. Immediately after the space probe had flown by Pluto, astronomers used the Hubble telescope to look around for other objects that could be observed within the framework of the mission. The first of them, Ultima Thule, is a binary asteroid in the Kuiper Belt whose 2 components diameters measure 19 and 14 kilometers. It was closely passed by New Horizons on the 1st of January 2019. Another object was the asteroid 2014 PN70, measuring 40 kilometers across. It was passed by the probe in March 2019. Excitingly, apart from that, having traveled 8 billion kilometers away from Earth, New Horizons reached a great vantage point for better observation of the stars closest to the Sun, Proxima Centauri and Wolf 359. In April 2020, the spacecraft was also used for double-checking the distance to these stars. Apart from the objectives mentioned, this amazing mission stands a good chance of being able to reach quite a few more in the future. While the spacecraft keeps beaming back new images to Earth, we will be able to conduct research based on the photos of the celestial bodies it has already passed. For example, the pictures of Pluto's largest moon, Charon, taken on their brief encounter with the space probe. Several centuries ago, it was quite unimaginable to admit to discovering exoplanets. However, everything changed in 1992 when the Polish astronomer Alexander Wolszczan was studying the pulsar PSR 1257+12. It was noticed that its pulsation period was irregular, which was accounted for by the influence of two planets with a mass 4 times that of Earth. This hypothesis was later confirmed, which led to the conclusion that the first planetary system beyond ours had been discovered. There are 3 objects in that system, 2 of which have a mass similar to that of Earth and are comparatively close to their pulsar in the constellation Virgo. Due to the fact that it is rather remote from us and the conditions for sustaining life are poor, the PSR 1257+12 system is of little interest to scientists. Although its discovery led us to believe that the search for Earth-like worlds may eventually be a success. Just 3 years later, the first exoplanet orbiting a sun-like star was discovered 50 light-years away from Earth and was dubbed 51 Pegasi b. Just several years later, the number of confirmed exoplanets counted in dozens, and today there are 4173 exoplanets and 3096 different planetary systems, unknown to science. In addition, a great number of Earth-like objects is still awaiting the confirmation of their status, which is possible after a secondary registration with telescopes on Earth. The number of celestial objects of this kind in the entire Milky Way may well be over 100 billion, with about 1/5 of them bearing resemblance to our Earth. Interestingly, most of the discovered Earth-like exoplanets are located not very far from our system. ROS 128b, discovered in 2017 by European scientists with the help of the High-Accuracy Radial Velocity Planet Searcher, UNveiled. The object is located in the single-star system ROS 128, which is the 13th closest star to us. The object is a faint red dwarf with a mass of 0.15 that of the Sun. It was possible to discover this planet thanks to its gravity, which leads to minor variations in the stellar spectrum of its parent star. While observing these variations, HARPIS is able to spot planets around stars. In this particular case, it took the telescope approximately 10 years to collect sufficient data. Before discovering this planet, this effort paid off. ROS 128 bits became the second Earth-like exoplanet lying closest to us. It is located 11 light-years away from the Earth in the constellation Virgo. Apart from that, astronomers claim it to be the most moderate of all known exoplanets due to its mass, temperature, and its rather calm parent star. It takes this planet 10 days to orbit its star. It finds itself in the habitable zone since the temperature of the photosphere and luminosity of ROS 128 are low. It is also classified as an Earth-like type of planet, and at the moment, ROS 128b is one of the most likely candidates to be a potentially habitable exoplanet. Besides, research done in 2018 confirmed that its climate is favorable enough to sustain life. Another exoplanet on the list of Earth-like objects located closest to us is Gliese 667c. This celestial body is part of the triple-star stellar system Gliese 667 in the constellation Scorpius. It consists of 2 orange dwarfs and 1 red dwarf. The first 2 components, A and B, lie 12.6 astronomical units from each other, with the third component orbiting them at a distance of 200 in this system was discovered on November 29, 2011 in the Geneva Observatory with the help of the Doppler method. The object is 22.7 light-years away from the Earth and is the second exoplanet orbiting its host star. The mass of Gliese 667 stacked is about 3.8 times that of the Earth, while its temperature range may be rather similar to the terrestrial one. Modeling at the Planetary Habitability Laboratory, managed by the University of Puerto Rico, reveals that the average surface temperature of the atmosphere of Gliese 667 must be approximately 27 degrees Celsius. The planet receives about 90% of the energy compared to that received by the Earth from the Sun. Also, Gliese 667 stacked is almost certain to be locked into its orbit, meaning it faces its star with one side always facing the star. If the planet's orbit does not curve too little and its mass is not too big, the greenhouse effect produced by the rather dense atmosphere must be quite sufficient to create favorable conditions for primitive life forms. The next deserving object on our list is HD 855. It is an exoplanet orbiting the orange dwarf HD 85512 in the constellation Vela. Its star is a single K-type main sequence star with a mass of 0.69 times that of our Sun. As for its age, it is more than 5.6 billion years old. The exoplanet discovered close to it is located 36 light-years away from the Earth, and its mass is 3.6 times that of our planet. At the same time, HD 85512 bits is one of the smallest planets in the habitable zone. It was spotted in August 2011 with the HARP-HIS telescope. The supposed steady-state temperature of its surface is around 25 degrees Celsius. If the planet's atmosphere is identical to that of the Earth, its surface temperature should reach 78 degrees Celsius. It is also highly probable that there is liquid water on this celestial body, which is why, for some time, it was believed to be the most likely place where life would be discovered first. Apart from the objects mentioned, there is a number of other celestial bodies in space located quite close to us, which also boast some unique features. Many of them may well contain various life forms and maybe not quite as far from us as we would imagine. However, we should bear in mind that some half a century ago, man did not possess a tenth of the information known to us today, and in the future, the progress of our discoveries is going to escalate even more dramatically. For example, on December 18th, 2019, the K-OP Space Telescope was successfully launched in orbit by the European Space Agency. It is specifically aimed at exploring exoplanets using the transit method. It may be this spacecraft is to contribute to the list of Earth-like exoplanets, and it may become the telescope to first discover alien life forms in the universe. Science does not stand still, and every new day bears witness to the fact that mankind continues to actively strive forward. If this progress does not lose its momentum, sooner or later, we are bound to find an answer to the eternal mind-perturbing question. Are we alone in the universe? And I hope the answer we get will prove that life is not a mere accident, but a logical consequence of the evolution in our universe. As a rule, microquasars are X-ray binaries, that is, stellar systems made up of two components. One of them is a regular star, similar to our Sun, and the other component is a compact object like a black hole or a neutron star. Matter in such microquasars is constantly in the process of accumulating in the compact object, which is accompanied by occasional outflows of matter at great speeds. These outflows are known as jets, and the nature of these jets reminds one of processes taking place in regular quasars. Now, it is not a regular occurrence in ordinary quasars. Meanwhile, as the mass of a microquasar is smaller than that of an ordinary quasar, jets may originate here practically on a daily basis. The principal difference between microquasars and ordinary quasars is in their mass and the frequency of matter outflows. For example, the mass of the compact components in microquasars is considerably smaller than the mass of those in regular quasars. It is just several solar masses. Just to compare, the average mass of a supermassive black hole in the center of a quasar may be approximately as much as 100 million solar masses. As for the mass of the black hole likely to be found in the center of SS 433, it must be just a few dozen solar masses. The accretion disk of a microquasar is intensely luminescent, with emissions in the optical and X-ray bands. A regular quasar is an astronomical body boasting the highest luminosity among other objects in the observable universe. According to contemporary scientific views, these celestial bodies are active sucks in matter all around it, thus forming an accretion disk. As for the disk itself, it is a source of very powerful luminosity. Just to give you an idea, its luminosity may sometimes be hundreds of times as intense as that of all stars in a galaxy like ours combined. To date, over 200,000 quasars have been identified. We're able to observe some of these quasars in the sky even without using a telescope. And so, the rate of discovering new objects of one or the other category is another principal parameter by which regular quasars and microquasars differ. If we look at the list of known microquasars, it contains just a few entries. So far, the first microquasar was discovered back in 1978 when a source of unusual radio and X-ray emissions was detected by two astronomers from the University of Cambridge as they were looking for debris left over from supernovae detected in the constellation Aquila. This source was later dubbed SS433. The object under scrutiny is an eclipsing X-ray binary system. One of its components is likely to be a black hole. As for the second component, it is a star of spectral type A, which is a main sequence dwarf star of a whitish hue. It is assumed that this star's mass is 10 to 30 times that of our Sun, and more likely than not, the dwarf used to be considerably heavier in the earlier stages of its existence. Its surface temperature is thought to be anything from 7,000 to 11,500 degrees Kelvin. This temperature range is typical for stars of this type. It is actually its temperature that gives the star its pale yellow tint. In fact, if we look at the stars closest to the Sun, then Sirius, Altair, and Vega fall into the same class as this star. S433 is located within the supernova remnant W50, sometimes also called the Manatee Nebula. The age of this nebula is estimated at approximately 20,000 years, and the distance between the nebula and the Earth measures about 18,000 light-years. The jets from SS433 distort the clouds surrounding the W50 nebula. According to a certain theory, the W50 nebula and the microquasar SS433 are actually related and came to be as a result of one and the same supernova event, which supposedly took place around 20,000 years ago. It takes either of the two objects in the system 13.1 days to orbit the common mass center. In fact, the way the SS433 system works is quite exciting, with both components constantly interacting with each other. Matter from the second component, that is, the regular star, flows to the first component or the primary, supposedly a black hole, thus forming an accretion disk around it. As it spirals, the matter heats up to extreme temperatures and emits X-rays. Some part of the matter leaves the system in two jets at the rate of approximately 26% of the speed of light, that is, 79,000 kilometers per second. In 2019, thanks to the ALMA Observatory, astronomers managed to get detailed images of SS433. It was clear from the emission structure that the microquasar's jets themselves are rather narrow and their shape is irregular and has nodes. Further studies of the object showed that the shape of the jets is distorted as a result of precession, that is, a process when the jets slowly rotate on their axis. As they spiral, the diameter of either of the two jets ejected from the microquasar in two opposite directions measures approximately 5,000 times the diameter of the solar system. Since SS433 is relatively close to the Earth, it is particularly valuable to scientists studying the phenomenon of microquasars. Images beamed back by the ALMA Observatory showed its jets for the first time, and also helped establish the direction these jets point out. It is never the same. Just like a top, the spinning toy gradually slows down. They too rotate on their axis, which is perpendicular to the plane of the accretion disk. The ALMA images boast of another outstanding feature. The shape of SS433 was predicted in fine detail thanks to spectroscopic measurements that had been done in 2018 using the Global Jet Watch telescopes. And so, the actual shape largely corresponds to the new images, where SS433 is really seen to have a shape reminding one of a corkscrew. It isn't a rare occasion when jets like that originate here or there in the universe. As a rule, jets of plasma, also known as relativistic jets, quasars, and radio galaxies. When this occurs, there are usually two jets, as such, pointing in opposite directions, and this is exactly what we can observe in the case of SS433. Today, the phenomenon of jets like that wants deeper studying. It is believed that jets originate following the interaction between magnetic fields and the accretion disk around a black hole or a neutron star. As for their size, it may be staggeringly enormous. In the case of the radio galaxy 3C120, for example, The jet stretches for at least several kiloparsecs away from its source. It is highly probable that in the future, the regular star in the SS-433 system will shed its outer layer completely as a result of the influence of the compact object. Its core, meanwhile, will remain hot, and thus the star will qualify to be called a hot subdwarf. Later, the star is to be gradually sucked in by the black hole, and sooner or later, after this process is completed, the SS-433 system will assume a classical look. It will comprise just the compact object. The process of this system's evolution will, of course, continue for thousands of years, so we have plenty of time to study this phenomenon. And while the microquasar at SS-433 is active, we will have many opportunities to carry out detailed observations that would help us understand the nature of this celestial object. Let's keep in touch. Predictably enough, the term intergalactic space is generally used to refer to parts of space between galaxies. It is believed that certain portions of these areas are practically devoid of any matter, which makes their composition quite close to that of absolute vacuum. With some areas stretching as far as millions of light years in all directions, intergalactic space is, for the most part, filled with ionized gas. Generally, this gas is hot hydrogen, whose density here is 10 times less than that in the interstellar environment, namely less than 1 atom to 1 cubic decimeter. There are also heavier elements to be found here as well, like carbon, oxygen, and silicon. Some parts of intergalactic gas are concentrated in clouds differing from each other very much in terms of density and temperature. Interestingly, the chemical composition of their gas is diverse. It may contain atoms of hydrogen, helium, carbon, nitrogen, oxygen, sulfur, and various metals. It is this gas that more likely than not feeds stellar formations in all galaxies. There are also much larger objects to be found in intergalactic space. For example, stars were spotted there quite recently. The total number of intergalactic stars in the observable universe may reach several trillion. Within the Milky Way alone, around 650 of these rogue stars have been pinpointed so far. As a rule, intergalactic matter doesn't emit any light and is mostly invisible to the potential observer. That is why its discovery was actually made by pure chance. It all started with quasars, which were discovered in the 1960s. Very soon, scientists noticed that the light from the quasars had certain missing pieces in some spectra. These particles were absorbed by something in between quasars and astronomers' telescopes. It later transpired that this invisible matter was the gas of the intergalactic medium, IgM. In the decades that followed, vast accumulations and filaments of gas and heavier elements were discovered in intergalactic space. And even though at first glance it appears to be empty, its dimensions are so mind-blowing that there must be more matter evenly distributed around it than there is matter in all the galaxies of the observable universe combined. It is safe to assume that some part of intergalactic gas has been left out there after the hypothetical Big Bang. Still, as there are heavier elements in its composition, it may only mean that many of these elements used to be part of interstellar dust lost by other galaxies. Intergalactic gas actually plays an important role in the process of the universe's evolution. Among all galaxies occurs thanks to this process. The point is that stars in a given area of the universe collapse and release part of their matter in intergalactic space. Having been released, the matter becomes part of intergalactic gas, and so later takes part in the processes of star formation in other galaxies. Consequently, star formation in galaxies will not stop. While there is still intergalactic gas around pulled by gravity, substantial portion of intergalactic gas is matter remaining after supernovae, which is why temperatures in some areas of intergalactic environments are extremely high, sometimes reaching as much as several million degrees Celsius. The high temperature of some areas may also be accounted for by a galaxy's gravitational pull. Gas is gradually drawn into galaxies at a rate of 1 solar mass per year. The rate of star formation in the Milky Way's disk is influenced by matter exchange in the intergalactic environment through stellar wind. This occurs when particles in a star's atmosphere accelerate to speeds exceeding the star's escape velocity. Stellar wind is crucial for stellar evolution as it causes a decrease in the mass of a star, which directly impacts its lifespan. Stellar wind can also carry matter over long distances through space, affecting the surrounding matter by sharing kinetic energy. Observations of galaxies and nebulae reveal the effects of stellar wind. For example, the emission nebula NGC 7635, also known as the Bubble Nebula, has assumed its shape due to this process. Similarly, in the case of the galaxy N82, also known as the Cigar Galaxy, matter rejections caused by stellar wind from numerous stars can be seen. In addition to the debris left over from supernovae, intergalactic dust is also present in this environment. Intergalactic dust has properties that can interfere with distance estimations on an intergalactic scale. It can form clouds and has been detected in several nebulae within several megaparsecs from the Milky Way. Detecting and exploring intergalactic stars is challenging. Some have been observed in the X-ray spectrum using telescopes like the Chandra X-ray Observatory. Many of these stars are part of binary systems, with one regular star and one compact, heavy object like a black hole. The more massive component attracts matter from the regular star, forming an accretion disk. This disk compresses and heats up, emitting X-rays. Rogue stars and voids may be more common than previously thought, and it is estimated that about half of the starlight emitted may come from stars beyond the boundaries of galaxies. However, it is currently difficult to determine their exact numbers, and it is unlikely that humans will be able to visit these remote areas in the near future. Objects in intergalactic space hold scientific interest, and perhaps in the future, advancements in technology will allow scientists to study this region more comprehensively. The earliest theory of the universe's origin was the steady-state universe, proposing that the universe has always existed in a state of equilibrium without a beginning or an end. However, scientific estimations and observations have disproven this theory, showing that irreversible processes occur in the universe. In the 1910s and 1920s, the Big Bang theory was formulated, which is now widely accepted. This theory explains the genesis and evolution of the universe and has been contributed to by numerous scientists, including Albert Einstein and his work on the general theory of relativity. The theories related to dark energy and the fate of the universe are still not definitive. Various theories exist, each with their strengths and limitations. According to current data, the age of the universe is estimated to be slightly less than 14 billion years, calculated from the moment of the Big Bang. The universe is continuously expanding, and depending on the density of dark energy, it will either continue to expand at an increasing rate or eventually slow down and reverse, leading to a compression into a singularity. Two possible scenarios for the future of the universe are known as the Big Rip and the Big Crunch. In the Big Rip scenario, the expansion rate of the universe would constantly increase, causing galaxies, star clusters, and eventually even atoms to be torn apart. Matter would cease to exist, and physical laws as we know them would no longer apply. The fate of the universe is highly uncertain, as we are still not fully aware of the nature of dark energy and its unknown to us at this point, and these may reverse the expansion processes. As a result, the universe will start contracting. This may well happen if general gravitation, created by all matter in the universe, exceeds its expansion force. This scenario is what is known as the Big Crunch. In this case, processes in the universe will run in the same manner until its size decreases 5 times. Galaxy clusters will come together as one supercluster, which will essentially fill the entire universe, considerably shrunk by this point. Meanwhile, inside the galaxies, events like births and deaths of stars, planet formation, and so on will keep taking place, just like before. When the universe contracts 20 times more, its volume will account for just 1% of that of today's, and all galaxies will blend into one. The relic radiation temperature by that time will measure 274 degrees Kelvin, and it will still continue to grow. This means that there won't be any liquid water left in the universe, and water is vital for biological life as we know it. Further contraction of space will cause the universe to heat up even more. Planets will first be burnt and then melted. All matter will crumple into an enormous cloud of boiling plasma. After that, atoms and subatomic particles will disperse, and eventually, the universe will collapse into a singularity similar to the one it used to be when it was born. There is a theory, which is a kind of a spin-off of the Big Crunch theory. It is known as the Big Bounce theory. According to the Big Bounce theory, on reaching the state of singularity following the Big Crunch, The universe will be reborn as a result of yet another Big Bang, and the cycle will repeat itself again and again, supposedly forever, as far as it is possible to speak about eternity in conditions devoid of time and space. I will repeat myself yet again by saying that our knowledge about dark matter is too meager to speak about the duration of any of these scenarios. For all we know, the next big rip or big crunch, for that matter, will take place in a period when there are still stars and planets around. But what if it isn't the case? What will happen to the universe if its ultimate fate is still extremely remote in time? Still, the laws of physics imply that the universe, as we more or less know it, cannot exist forever. There are 4 clearly defined epochs in cosmology, and each of them is associated with this or that particular phenomenon. We live in the so-called stelliferous era. There is a lot of interstellar gas in the parts of the universe around us. It is used as raw material for stars to form from, and new stars are born from this gas, and the process will continue until all interstellar gas has been depleted. This epoch is expected to be over in the period from 1 to 100 trillion years from now. By that time, the Sun and the overwhelming majority of other stars will have depleted their nuclear fuel, subsequently turning into white dwarfs, neutron stars, or black holes. I've actually already spoken about it in an earlier video. The next era is known as the degenerate era. In the future, most main sequence stars will no longer exist. Instead, the universe will be filled with white and brown dwarfs, as well as neutron stars and black holes. These objects will gradually cool off over an incredibly long period of time, on the order of 10·39 years. White dwarfs will emit radiation and become black dwarfs, while brown dwarfs will cool off and eventually stop all reactions. As the universe continues to evolve, most matter will be absorbed by black holes. At this stage, the major processes will be dark matter annihilation and proton disintegration. Protons, which are subatomic particles that make up atoms, have a lifespan of around 10·41 years. As the universe progresses towards its end, it will resemble an ocean of elementary particles, with the occasional neutron star or black hole. The next era is the black hole era. Some theories suggest that black holes will merge together to form a single colossal black hole, while others propose that black holes will gradually evaporate through Hawking radiation. This process of black hole evaporation is projected to occur over 10·100 years. Eventually, only vast expanses of dead space will be left in the universe, filled with remnants of past processes. In this state, photons, electrons, positrons, neutrinos, and quarks will continue to exist. Electrons and positrons will collide and annihilate each other. The universe may persist in this state indefinitely, until the possibility of a big crunch or big rip. However, the fate of the universe is uncertain, and whatever happens, humanity will likely our planet will remain habitable for another billion years or so, after which it will be consumed by the expanding sun. About 5 or 6 billion years in the future, our sun will transform into a red giant and eventually become a white dwarf. As for what happens after the death of the universe, it is impossible to say. There will no longer be time or space as we know it. Even if scenarios such as the Big Bounce or Big Crunch occur, we will never be able to find out what comes next. The universe will be shrouded in darkness and silence. It's important to note that the information presented here is just a small glimpse into the incredibly vast and diverse phenomena of the universe. Scientists will continue to study and update our understanding of these phenomena for centuries to come, providing us with even more exciting discoveries. Let's stay connected for future updates.